Hello and welcome to our next lesson in our Sequences and Series unit regarding arithmetic series. So far we have taken a look at patterns of numbers. We've taken a look at arithmetic sequences as well as geometric sequences. Today we're going to talk about what is meant by this different word series, and we're going to look at just the arithmetic series today. If we were to look at a pattern of numbers that would go 2, 4, 6, and so on, so 2, 4, 6, 8, 10, 12, this is a predictable pattern of numbers. It is an arithmetic sequence. A is always our starting value. It is a 2, and we have a common difference denoted by the letter D, that we are constantly adding a 2. And we know from the past lesson that any number, term n, in a sequence that is arithmetic, we can calculate its value by taking its starting value and adding a bunch of differences. N minus 1 just means one less time than the term you're looking for. So if you're looking for term number 20, you would calculate its value by starting at your first term and adding a bunch of differences 19 times to get to the 20th term. Excuse me. And that would give you each of the individual numbers in the sequence. But a lot of times we're not interested in just the numbers of the sequence. We're interested in what the pattern adds to. And so if we are looking at 2 plus 4 plus 6 plus all the rest of the numbers in the sequence up to whatever value we're interested in, we would call that an arithmetic series. And so there is a very big difference in terms of what is meant in the words sequence and series. Now I gave you a example of a real world arithmetic series in the handout, where I asked you to take a look at a fun pattern of savings. This is called the 52-week money challenge, and the pattern is that on each of the week numbers you would save that number of dollars. So on week 1 you'd save $1, week 2 $2, and so on, all the way up to week 52 you'd deposit $52. And I asked you to puzzle through what would the final total value of the money, the entire pattern. We don't care, well, I mean we do care, but it's not so much the numbers in the pattern that we're wondering about. We want to know, what does it all add up to? What is the total that I would save? So I hope you've had some fun going through there. And now what I want to do is talk to you about perhaps an easier way to get to that total, where we will look at how we can develop an equation to solve the sum of the pattern or to solve the value of the series of an arithmetic series. So a series is the sum of the terms of a sequence. The sum of the first n terms is denoted not with a t, not with the term number, but the sum of a certain number of terms in that sequence. So we would go the sum of 3 terms, or the sum of 16 terms, or in this case, the sum of 52 terms in the series. Now this was actually puzzled out by a precocious child at the age of 8 named Carl Gauss, and he figured out the general formula for how to calculate the sum of the patterns of numbers in an arithmetic sequence. And there's a couple ways to come about this, but this is the way that he decided he was going to logic it out. He wanted to know the sum of the first 100 natural numbers. So natural numbers are, of course, the whole numbers, 1, 2, 3, 4, 5, and so on, excluding the 0. So if he wrote them out in a pattern of 1 up to 100 digits, what he decided to do was to pattern them out in reverse. And so he patterned out 100, and try to keep these numbers below each other, 99 plus 98 plus 97 plus 96 plus all the numbers in between, and he put them right below each other. So under the 100 would be 1 and 2, 3, and so on. And what he did is he saw that each of those pairs added to 101, 101, 101. And so he add the two sequences, sorry. Oh, I guess it is a series because I'm adding the two series, the addition of these terms. And so what he had was the sum of 100 terms, but he was going to have double the pattern. He was going to have two sums if he added them this way, and he had 101 from those two terms, and 101 from the second two terms, and 101, and so on. And down here for these ones as well, 96 and 5, 101. And he reasoned out that if he doubled up his pattern, he would have 100 terms of 101. And so his double pattern, the twice the sum of the 100 first natural numbers, would be 100 terms that were each worth 101. Well, 100 times 101 is 10,100. And so we would have double the pattern of the sum of the first 100 numbers. And then if we just wanted to divide away that 2, the sum of the first 100 numbers would be the total of the patterns divided by 2. And so he found that if he wanted to know the sum of the first 100 natural numbers, the sum of the first 100 numbers in this sequence would be 5,050. And so if we take a look at this specific set of numbers here, if we go back to here and we sort of pull this apart, we could say that the way he analyzed this for his sum of 100 natural numbers was to take the number of terms, his 100 terms. We want to figure out how to generalize this to any situation of any arithmetic sequence. And in his first term that came to 101, he got that from the very first term of the sequence and added it to the very last term, which he patterned out in reverse. So 1 plus 100, that's how he got his first 101. So this was the value of term 1. And this one was the value of the last term, or the nth term in the sequence. And then he took that and divided by 2, because that was double the pattern. Now, if we divide by 2 here, we would get 50. And so he had 50 values of 101. In general, we can sort of generalize this to apply to any arithmetic series by saying, all right, you want the sum of any number of terms in an arithmetic sequence? Well, this is our number of terms. We've always called that n. And our n is a whole number, and it's going to be divided by 2. I mean, the whole thing is going to be divided by 2, but I could reduce here. So let's say n over 2. Multiplied by the value of the first term. We've always called that the letter a. And then the value of the last term, we know, can be denoted by term n, which would be, in this case, term 100. And so we have half the number of terms for the first and last term. And there, folks, is the general formula for calculating any arithmetic sequence. Now, I hope you've seen that your 52-week savings jar, if we go back there, I'm not sure if you put all of the individual values in there and did your running total and got the total yet, but let's just take a look at our 52-week savings. We have 52 weeks, or 52 numbers. Here's our sequence, 1, 2, 3, 4, 5, 6, and we took that 1 and added that 2 and added that 3 all the way up to term 52, which was adding that 52nd dollar. And so I suppose I could do, that's a little inconsistent, our 52nd dollar. So that was term 1, term 2, all the way up to term 52. Well, we now know that we can liken this to the equation that we just, or use our equation we just built, that if I want to find the sum of any number of terms in an arithmetic series, then I will take the number of terms, divide by 2, and multiply that by the value of the first term added to the value of the last term. And so in this situation, the sum of my 52 terms in this sequence, well, I have 52 terms divided by 2. My first term was the $1, added to my last term, which is the $52. And so in this case, we have 52 divided by 2 times my 53. And so 52 divided by 2 times the 53 is $1,378, which is a heck of a lot easier of a way to getting the total of this entire pattern. If we were to save in this manner, we could keep a running tally, or we could calculate it out using our new arithmetic series formula. So the formula for the sum of the n terms in the arithmetic sequence, we wrote it here, but there's a space for it here as well. Take the number of terms, divide it by 2, and multiply that simply by adding the first to the last term, or the value of those. This formula, however, is only useful if we do know the first and the last terms. And we'll see that in some situations we don't always know the value of that last term, and we'll see how we can cope with that. So here is a very simple kind of entry-level question on these. If I have this pattern of numbers and I'm adding them, I have a series, find the sum of the series. Well, in this case, I know my A value. I know that A is 2. And in this case, I know that the value of the last term is 62. My problem here is I don't know what n is. I don't know how many terms are in this sequence. And so the first thing I need to do, oh, and the other thing I do know is I have a common difference. I am adding 5, adding 5, adding 5, all the way through this pattern. And so now I know I have a common difference of 5, and that's what defines it as an arithmetic series, because we have that addition of a common difference. Okay, so the first thing we need to do, because I know that I'm going to be using this equation, n over 2 times a plus tn, and at this point I know I have the over 2, and I know that I have a 2 plus a 62 in these unknown spots, but what I don't know is how many terms I'm adding up. Well, what is useful is to draw on our previous lesson about finding the value of each term in an arithmetic sequence. So to find any term value in an arithmetic sequence, we would start at our starting value, add a bunch of differences, n minus 1 times. At this point, I know the a, I know the d value, and I could use any known term. And so with this one, if we want to use our tn as our last term and find out its term number, we would put its value here. Our a value is 2. Oops, sorry. A value is 2, adding a bunch of differences of 5. I'm not sure how many times I added the 5 to get to the 62, but I sure can solve for it now. One of the biggest common order of operations mistakes here is I'll get kids who will add this 2 and 5 to make a 7 and then divide by 7. Please don't do that. Remember, when you're solving algebraic equations, we undo bedmiss, so let's kick out this 2 first. We'll subtract 2 from both sides, and so I get 60 is equal to 5 times that n minus 1. Now I can divide by 5 on both sides, and I get the fact that we have 12 is equal to an n minus 1, and then we just add that 1 to both sides to get that, hey, this is the 13th term. N is asking for or denoting that this is term number 13 is worth a 62, and so I know I am looking at the 13th term. Because now I know I'm adding up 13 numbers in the pattern for my series, I'll have 13 divided by 2, which is 6.5, and 6.5 times 64, if we put that in our calculator, we will find that that comes to 416. So if I was to add the 2 plus the 7 plus the 12 plus all the numbers in between and getting to adding that last term of 62, that whole pattern, even though I don't know the middle numbers, I can figure out the whole pattern would have a sum of 416. Okay, what if I don't know that last term? What if I was told, hey, here's my pattern. Add up the sum of the first 13 digits, or however many digits, and in this case it was 13. If I don't know the value of that last term, I can always create or use a second formula because I know the formula for this piece here. I know that for any arithmetic sequence, the term of any arithmetic sequence, if I don't know the last term, it can be calculated by starting at your start value, adding a bunch of differences, n minus 1 times. And so what I can do is insert this formula into this equation that we built to find that I could build a second equation that would be useful if I didn't know the value. I could calculate it. I mean, I could do this in two parts. I could calculate it and then put it in. However, I can create one equation that I can put in this equivalent numerical value or equation here, that a Tn is equal to an A plus a D times n minus 1. And let's simplify this. We have A plus A. And so I have 2A plus D times n minus 1. And that is probably the most useful version because I don't have to know the value of my last term. It will automatically calculate it as I input the variables in here. I do need to know that A is the value of the starting term. D is the common difference. And N is the number of terms that you're adding in the sequence. You have to know those. And so the most valuable is to take n over 2 times 2a plus d times n minus 1 because it will help you out in any situation. You don't have to know the value of that last term. So here is an example of a couple of arithmetic series. This one is going up, this one is going down. And so find the sum of the first 12 terms. So I know that my n is going to be 12. I'm starting out at a value of 13. It looks like I am have a common difference, and if we want to calculate, if it doesn't pop right out into your head, remember that the difference can always be calculated with any term and we subtract the one previous. And so if I subtract 13 from 24, I get an 11. And just to see that it is in fact a common difference, that it's happening over and over again, we can take that 35 and subtract the 24. And again, I get a difference of 11. So this is our common difference in the pattern. So my common difference is 11. And so now I'm going to use my most valuable equation here because I don't know the value of the last term. I would have to go calculate it separately now and then use my original equation. But if I use this second equation, I can calculate it directly, that the sum of 12, actually let's write our general formula here. The sum of any number of terms in an arithmetic sequence is n over 2 times 2a plus d times n minus 1. The number of terms divided by 2, double your first value, and then add a bunch of differences one less time than the number of terms you're adding in the pattern. Here we are adding 12 terms in the pattern, so it's going to be 12 over 2 times 2 times my starting value, which is a 13, added with a difference of 11. How many times? Well, 12 minus 1 times, so 11 differences to get to the 12th term in that series. If we simplify this, we have 6 times 26 plus 121. We get 6 times 147, and 6 times 147, the sum of the first 12 terms in this pattern is going to be 882. Find the sum of the first 54 terms, so we know n is 54. The a value, we're starting out at a -7. And how am I getting from term to term to term? It looks like I am subtracting 4, and we could confirm it with our subtraction of negative 11, subtract a negative 7, or negative 11 plus 7 gets us to a minus 4, so a common difference of going down by 4 or adding a negative 4 each time. And so the sum of any number of terms, again, I don't know my last value, so let's use our more involved equation. Take the number of terms divided by 2, double up your start value, add a bunch of differences, one less time than the number of terms you're adding in the pattern. And so I'm looking for 54 terms in this pattern, and I'll double my start value of negative 7, add a bunch of differences of negative 4. That would be the same as subtracting 4 a whole bunch of times, so I could add the negative 4, or I could subtract 4 n minus 1 times, so 54 minus 1, or 53 times. And so I'm going to have 54 over 2 is 27, and I'll have a negative 14, subtract another negative 4 times 53 is 212, and so I'm going to have 27 times a negative 226, and so the sum of 54 terms, the sum of my first 54 terms in this arithmetic series is negative 6,102. Okay, so those are two illustrations, one where we had a positive common difference, one where we had a negative common difference. And where do these work into our idea of word problems or applying this principle to real world situations? Situations like this. We have a marching band. It has 8 musicians in the first row, 10 musicians in the second row, 12 musicians in the third row, and so on. If there are 12 rows of musicians, then how many musicians are in the entire band? So remember, on a unit test, all of our sequence and series word problems will be mixed together. And the first thing we have to ask ourselves here is, are we just interested in an individual number in the pattern, or are we interested in totaling up the pattern? And in this case, we are absolutely interested in totaling up the pattern, how many musicians are in the band. And so we'll use our arithmetic series formula. Why arithmetic? Well, I always think it is very important that at the beginning of any word problem to write down the pattern of numbers. And so here we start with an 8, and we're going to add a 10 and add a 12 and so on. And so if we take a look at that, we can see it's arithmetic because we have a common difference of 2 every time. And so my A value is 8. My difference is an addition of 2 every time. I am wondering about 12 rows of these musicians. That means I need to get to the 12th term in that series. And so my n value is going to be 12. And so if I pull out my arithmetic series equation, let's remind ourselves of this, reinforce it every time we write it down. I don't know the value of how many musicians are in that 12th row, but if I use my more involved equation, I don't need to know the value of the last term. And so how many terms? Well, there's 12 rows in the band. Divide that by 2. Let's double up our starting value, adding a bunch of differences of 2 musicians every time. If we have 12 terms, we'll have 12 minus 1 additions of that difference in common from row to row. And so we will have a 6 times a 16 plus an 11 times 2 would be 22. And so we're going to have 6 values of 38, which comes to my sum of 12 rows of these musicians is going to be 228 band members. And because it was asked in words, we always have to answer a word problem in words. There are 228 band members. Similarly, question with a pyramid of cards. Pyramid of cards has 5 cards in its top row. Every row under it has 4 more than the previous row. If there are 230 cards in the pyramid, how many rows are there? So a little bit of a curveball here. If there are 230 cards in the pyramid, we have been given the total number of cards in this situation. And so in this case, we know the sum of the number of rows in the pyramid is our 230 cards. We don't know how many rows there are. How many rows? That's our row number. That is our unknown. We do know that a pyramid of cards has 5 in its top row, so let's call that our first term. 5 in that series, and we have a difference of 4. So our pattern is going to be 5 plus, and with a difference of 4, there will be 9 in that next row, plus, with another difference of 4, 13, plus all the way up to the 200, oh sorry, all the way up to our last term. That is going to be equal to, if we add up that whole pattern, that whole addition will be 230. 230 is not a term in our pattern. 230 is the addition of all the terms in our pattern. So here, and we have to use our more involved formula because I don't know the value of how many cards are in that bottom row or that last term in the sequence. So we'll use our sum of the n numbers of terms in our sequence is the number of terms over 2 times the first starting value plus a bunch of differences, n minus 1 times. And when we put in all of the values we know that the total of the pattern is going to be 230. I don't know the number of terms in that pattern. I do know that I'm doubling up a first term of 5, and I know that I'm adding a bunch of differences of 4 n minus 1 times. And so we have n in 2 places, so we need to get busy getting that n into one spot. Now, I've written fairly large here, and I'm going to have to start writing small. I've forgotten how long that this solution is, so please write small with me here. 230 is going to be equal to n over 2, and we've got our 10 plus, and let's distribute this 4 into my bracket so I can liberate the n out of the bracket, 4n minus 4. So 230 is equal to n over 2 times, we'll have 4n plus 6 in that bracket. And so now what I need to do is distribute this term, whatever my mystery number is divided by 2, we'll distribute that into my bracket. Here, let me zoom in. And so, again, writing small, I'll have n over 2 times a 4n. So I'll have 4 in my numerator and n times n in my numerator, so n squared, and I'll have a denominator of 2. So that will simplify to 2n squared, added to a 6 times an n over 2. And so 230 is equal to 2n squared plus 3n, and we have a quadratic equation. Of course, from grade 10, we know that to solve any quadratic equation, we set it equal to 0. So let's subtract this 230 from both sides. And now we could factor that, but we could run it through the quadratic equation if we can't sit here and factor, but it is a factorable quadratic. And with a 2n times n, we could get to 2n squared. And what two numbers multiply to negative 230? But yet I would get an inside-outside value of just 3n. So I should have a sense that these numbers are going to be fairly close together if my inside and outside term is going to come to 3n. And if we played with it long enough, we would in fact find that 23 times 10 gets me to a 230. I need it to be a negative 230 with a positive 3n, and this 2n times 10 is going to be 20 n's. And so if I subtract 20 n's from my 23 n's, I find that I have a factorable situation here. Now, both of these are going to provide me with answers of what values of n could make this quadratic equation 0. And so I would continue down here if I had room, but let's just go and take a look at both of these factors. Remember, with the zero product property, we turn an addition of terms into a multiplication of factors here, which allows us to use our zero product property, that in order to make a 0, I only have to make one of these values a 0. So this one is the easiest. How would I make n minus 10 equal to 0? Well, let's add that 10 to both sides, and in fact n could be equal to 10. So our term could be 10 terms, our term number, how many rows of cards in the pyramid, could be 10. If we took a look at the other possibility, our 2n plus 23 being equal to 0, well, 2n being equal to negative 23 and n being equal to negative 23 divided by 2 would be negative 11.5. That's not valid. It's not valid to have negative 11 and a half terms in a sequence, and so that one doesn't make any sense to our situation, but to have 10 rows of cards in a sequence absolutely would make sense. So therefore, there are 10 rows of cards in this pyramid. So sometimes we might be solving a quadratic equation out of one of these trickier types of questions. Okay, so today what I would like you to do now is to move on to your homework. Page 469 in our textbooks. There are some at the side of the room if you would wish to borrow them for the period. However, I have put the odd questions for 1 to 4. Certainly if you want to do more of a particular type of question, I would think it was very valuable, but this is the minimum that I would like you to practice with. So have fun with that, and we will do a check your understanding at the beginning of next period to see how well you did with this. Thanks, and we'll see you soon.